The dream of escaping our planet has fascinated humanity for centuries. But to get off the ground, we need to overcome one major technological hurdle: gravity. Even if we could design spaceships that are up to the task of traveling through the vacuum of space, they would never leave Earth's atmosphere without a tremendous amount of energy. And no existing technology can provide enough of it. So what is stopping us from entering the solar system's great expanse? Hey there, welcome to Life Noggin. Today we're talking about how to overcome gravity. In order to understand how to beat gravity, we have to understand how it works in the first place. The force of gravity depends on the mass of the object and how far away it is. Sir Isaac Newton developed an equation to calculate this force between two objects like the Earth and you. As long as these objects aren't moving at crazy speeds or undergoing any other major forces, Newton's universal gravitation equation states that the force of gravity between them is equal to the product of their masses divided by the distance squared between their centers. So, the more massive an object, the stronger its gravitational pull. But also the closer you get to it, the stronger the gravitational pull becomes. This means that the Earth's gravitational pull isn't just determined by our planet's mass, but also by how close we are to it. At the surface, we feel the full force of the Earth's gravity. But as we move away, the force decreases rapidly. If you were to double the distance between you and the Earth, the force of gravity would drop to 1/4. If you were to triple the distance, the force would drop to 1/9. And this happens very quickly. Most of the Earth's gravitational pull is felt within just a few thousand kilometers of the surface. But the Moon, which is about 8 times farther away, still exerts a measurable gravitational force. That's because even though the Moon is much smaller than the Earth, it's still fairly close enough to us to exert a noticeable pull. And in fact, astronauts on the International Space Station are actually orbiting the Earth in a region where the combined gravitational forces of the Earth and the Moon are cancelled out, making it easier to maintain their orbit. So even though it might not seem like it, we're actually pretty far away from the Earth's gravitational pull. The ISS is around 400 kilometers above the Earth's surface. From that altitude, the force of gravity is only about 1/6 of what it is on the surface. And the further we get away from the Earth, the less its gravity will affect us. Eventually, if we were to travel so far away that the Earth became just another star in the night sky, its gravity would be indistinguishable from all the other stars. And with that, we've escaped the Earth's gravitational pull. But while it may be easy to escape the Earth's gravity in theory, in practice, we haven't figured out a way to do it yet. The biggest challenge facing space travel today is overcoming the Earth's gravitational pull. Rockets are designed to burn fuel and generate thrust, which allows them to lift off and reach higher altitudes. However, the higher they go, the thinner the atmosphere becomes, meaning there's less air for the rocket to burn and less thrust it can generate. For example, NASA's Space Launch System, which launched the first of the Artemis missions to the Moon in 2022, uses hydrogen and oxygen as its propellants. These are some of the most powerful and efficient rocket fuels available. When burned together, they produce tremendous thrust, allowing the rocket to accelerate to incredible speeds. During the first stage of flight, the SLS generates over 8.8 million pounds of force pushing the rocket upwards. That's equivalent to the weight of almost 97 fully grown African elephants. However, as the rocket climbs higher and higher, the atmosphere becomes thinner and thinner. This means that the rocket's engines can't burn as much fuel as they would at sea level. In fact, by the time the rocket reaches the top of its trajectory, it'll be traveling through space where there's no air at all. And because there's nothing to burn, the rocket engine will stop working altogether. That's why rockets need to carry all of their fuel with them. They can't just go to a gas station in space to refuel. So how much fuel does a rocket need to escape the Earth's gravitational pull? Well, it depends on how much mass the rocket has. The more massive a rocket is, the more fuel it needs to escape the Earth's gravitational pull. This is because the force of gravity depends on the mass of the object. The Earth's gravitational pull is so strong that it takes a lot of energy to break free from it. According to Newton's laws of motion, work is equal to force times distance. So, the more massive a rocket is, the more work is required to move it out of the Earth's gravitational pull. This means that the heavier a rocket is, the more fuel it needs to escape the Earth's gravitational pull. To make matters worse, as the rocket accelerates, its mass increases. As it gains speed, it also gains momentum. And according to Einstein's theory of special relativity, mass is a measure of an object's energy. So the faster a rocket goes, the more massive it becomes. And the more massive it is, the more fuel it needs to keep accelerating. This means that a rocket needs an infinite amount of fuel to go faster than the speed of light. Since nothing can travel faster than light, this means that no rocket can ever escape the Earth's gravitational pull completely. Luckily, we don't need a rocket to go faster than light to escape Earth's gravitational pull. We just need one that gets fast enough. In 1961, Alan Shepard became the first American to travel into space aboard a Freedom 7 rocket. It took about 5 minutes for his Mercury capsule to reach an altitude of 116 kilometers. Now, that's not very high when you consider that the Earth is almost 6,400 kilometers wide. But it was enough to make him an astronaut. That's because getting into space doesn't require a rocket to escape the Earth's gravitational pull completely. It just needs to get high enough. Anything that reaches an altitude of 100 kilometers or more is considered to be in space, regardless of whether it's still under the influence of the Earth's gravitational pull or not. This means that a rocket doesn't need to be traveling at infinite speed to escape the Earth's gravity. It just needs to be going fast enough to reach an altitude of 100 kilometers. Shepard's Freedom 7 rocket did just that. It reached a top speed of 28,000 kilometers per hour, which allowed his capsule to reach an altitude of 116 kilometers before it began to fall back down to Earth. But it wasn't just any old fall. It was a carefully controlled descent that brought the capsule down safely in the ocean, where it was recovered by a Navy ship. So, although he never quite escaped the Earth's gravitational pull completely, Alan Shepard was still able to go to space. It's really cool that we've managed to figure out how to get to space despite the limitations of physics. It shows that with enough ingenuity, we can accomplish anything. Now, check out another video we did about how to get to space. What do you think? How else might we overcome gravity in the future? Let us know your thoughts below. As always, this has been your host. Don't forget to keep on thinking.